The paper I'm introducing today is learning to detect objects from multi-agent LiDAR scans without manual labels. Let's start from problem description. Given a point cloud seen from a car LiDAR, we want to find all the bounding boxes of nearby cars. And there's the good news. This is a multi-agent dataset. So we have informations from different cars nearby. So we can integrate point clouds from different position and different viewpoints. There are two main challenges of this topic. The first one being the labeling can be expensive. The second one is how we can efficiently utilize information from different agents. If we only use the point cloud from a single viewpoint, a single position, we only get partial points like this, and it will be hard to predict the right bounding boxes by these viewpoints. So let's look at the method. Training step 1, initialization with shared info. As mentioned earlier, we have a few collaborating cars that will share their information with us. So we know their position, their orientation, their model, their dimension. So as a result, we know their bounding boxes. We will use these bounding boxes to train the first version of our model. But of course, there are a lot of other cars that don't share information with us, but for now, we just ignore them. And there's training step 2, preliminary label generation. We will now use the first version of our model to generate labels. We will set the confidence threshold very low, so it will produce a lot of prediction bounding boxes, but a lot of them are false positives. It's okay, we'll fix them later. The reason is we want to include all possible candidates here. And then there is the third step, multi-scale scale bounding box encoding for label filtering. As mentioned earlier, we have a lot of false positive, and we want to filter them out. The author used 3 methods to filter out bad prediction. The first one is collision check. Is the object in the box a separable object? Let's take a look at the bounding box here. This bounding box mistakenly take a wall into a car. So as we can see, the wall is not separable. It peers through the box. So what we do here is we make the box slightly larger and see if there are new points being included. If there are new points being included in the larger box, it means the object inside the box is not separable. It's not a car because a car is separable. So this is a bad prediction. The second method is boundary alignment. Is the box too loose? So let's take a look at the right box here. It indeed includes a car, but it's too large. So what we do is we make the box slightly smaller and see if there are points originally inside the box being excluded. If that is the case, it means there are a lot of space, so the box is too loose. This is also a bad prediction. The third metric is distance confidence. So in general, if a box is far away from the observer, the confidence level will be lower. So using these 3 metrics, we can filter out bounding boxes with low confidence. And finally, unsupervised learning. So using the good labels from the previous round, we can train the model. And similar to YOLO, model generates confidence level as well as box attributes. The author also includes an auxiliary loss called contrastive loss. This is similar to the triplet loss we introduced in class. We want to make sure the features of the good predictions are close to each other, while the feature of the bad predictions stays away from them. And then we loop through step 3 and step 4 until the model converges and this unsupervised learning is done. So unsupervised learning kind of solved the first problem. The labeling is too expensive. But for the second problem, integrating informations, we will use the method mentioned here. So we could try to combine combine point clouds from different agents, but that doesn't work well in real-world data. That is because data transmission can have delays in GPS or the relative position, orientation. They can have errors, they can have deviations, so they are not very accurate. So the combined point cloud is low quality. The author instead did this in feature space. They use attention layer to combine features from different agents. And as a result, when agents are communicating, they do not send point clouds directly, but the intermediate feature they computed. This is the experiment that tested on two datasets, one real-world dataset and one simulation dataset. As you can see, the proposed method is significantly better in IOU score than previous methods. And this is the main contribution of this paper. They proposed an automatic labeling pipeline for multi-agent point cloud card detection. And the proposed pipeline outperforms previous unsupervised methods.